So most of you might be civil. This is mostly like geospatial stuff. So again, feel free to stop me at any time. I'll start with an introduction to the project, tell what it has to do with work going on in the Suite Lab here at PSU, go over a quick background and literature review, introduce our problem statement, the project we worked on in Cedar Creek with the Freshwater Trust in Springfield, go over the Freshwater Trust monitoring and data analysis procedures and the results they were able to receive from their first year. Then I'll go over the method we developed for biomass monitoring with an unmanned aerial vehicle, or UAV, how we were able to collect, calibrate, and analyze the data, and then compare it to the Freshwater Trust data, and the conclusions we were able to draw. So the inspiration for this project came from a study that the Suite Lab is involved with in Rwanda. Del Agua, which is a private sector company, distributed cook stoves and water filters to 300,000 of Rwanda's poorest households. The cook stoves use 50% less wood than traditional three-stone fires, and the water filters eliminate a need to boil the water. Rwanda is 98% deforested, so this intervention is predicted to have a 10% national wood use reduction, and they have to figure out how to measure that. So typically enumerators go out and measure the diameter and heights of trees in a study site before and after the intervention. Those assessments have restrictions like time, money, personnel, and have methodological limitations like geographic coverage, enumerator bias, and also a significant time lag in between study implementation and data analysis. So we did some research and found out that we could take those measurements with a UAV. But developing that method in Rwanda wouldn't be feasible. So we got in touch with the Freshwater Trust, which is a local conservation company here in Portland. They do work to preserve and restore freshwater resources. One of their main areas of focus is riparian restoration. Riparian zone, which most of you know, is the interface in between land and a river or stream. The goals of these projects are to protect, maintain, and restore fish and wildlife habitats along with water quality and quantity. Rapid assessments of these projects are needed to objectively and reliably show how the funded efforts are doing. A lot of research around riparian restoration that's been done lately shows that the monitoring process needs improvement in order to show how the projects are doing and show a detailed analysis of the vegetation. Those limitations led us to say, okay, let's try and do this with the UAV. And the way we would do that was using structure for motion. So structure for motion algorithms take digital images collected from the UAV and they're able to create a 3D point cloud. Structure for motion uses feature matching to create the 3D point cloud and predict where the images were taken. So it establishes key points on each image that are constant throughout the photo series, even under lighting and viewpoint variations. These key points are used to create descriptors that are then put into a bundle adjustment system that creates the 3D point cloud and estimates the camera locations. The 3D point cloud that's created is similar to that of LiDAR, light detection and ranging technology. LiDAR is a remote sensing technology that calculates the distance to an object by taking the speed of light times the amount of time it takes a laser that's emitted to reach that object to create a point cloud. LiDAR has been proven to be able to estimate heights, locations, and canopy cover of above ground biomass. So the techniques used on a LiDAR point cloud, we used on a UAV generated point cloud. This study was done by Edson and Wing from OSU, where they analyzed the ability of LiDAR to locate and measure trees in a forest stand. We used some techniques used in that study in our study. Recent research using UAVs to monitor, evaluate, and manage restoration projects has been looked at greatly over the past 10 years. Utilizing UAVs for biomass, forest, natural resource, and vegetation monitoring have been shown to have significant temporal and spatial resolution impacts at a much lower cost than typical monitoring processes. This study, done by Fritz et al. In 2013, they took a UAV and built a point cloud of open forest stands and compared it to terrestrial laser scanner point cloud. The UAV generated point cloud was much less accurate and complete, but it correlated well with an Pearson's correlation coefficient of 0.69. This showed that UAVs had a high potential for forest monitoring, but also showed that there's still a lot of room for more research. In this study done by Zarco et al. In 2014, they analyzed the ability of a fixed-wing UAV to create digital surface models and orthomosaics and compared it to field measurements of 152 validation trees to give an R-squared value of 0.83 and a root mean squared error of 35 centimeters. This showed that a digital surface model created from a UAV had a high potential for monitoring purposes, and it could be accurate enough. So for our study, our problem was that the freshwater trust riparian restoration monitoring procedures produce really low resolution data and takes excessive time, money, and personnel. Their analysis process from when they go out and count trees, collect data, to the time that the data is available is about 6 months. That's way too long. So our solution was to develop a method for low-cost tree stem detection via UAV that produces stem count outputs using much less time with much higher spatial resolutions to improve the quality of data within all restoration projects. Our project was at Cedar Creek, which is in Springfield. The goals of the project were to restore riverbank stabilization, changes in flood flows due to dams, and provide necessary shade at a necessary temperature suitable for wildlife. The Freshwater Trust in 2015 planted about 6,000 trees and plants of 22 different species on a 2.02 acre plot along Cedar Creek, which is an offshoot of the Mackenzie River. This is an aerial view of the project. The pink is where all the plants were planted along the south bank of the river. So the Freshwater Trust monitoring procedures consist of about 2 to 3 people going out every year and establishing 7 20 by 20 foot plots. The plots are started at the yellow dots on this map. Those are the transect origins. They draw a line 20 feet perpendicular to the river and draw 2 10 by 20 foot plots on each side of that line. In these plots, they collect data on species and heights of trees in 3 height classes, from 0 to 3 feet, 3 to 7 feet, and above 7 feet. The data from these plots is then averaged to give 3 numbers for the entire site. So you have 0.5 to 3 feet. These are the results from the first year of the study. 0.5 to 3 feet, 1836. There's the most trees that are below 3 feet because they were just planted 1 year ago. 3 to 7 feet, 78 stems per acre, and above 7 feet, 70 stems per acre. These results are reported with 80% confidence intervals, which is not very good. It's giving for the entire plot, plus or minus 844 stems per plot, which is huge. So we were just trying to get within that confidence interval with the UAV. So after about 10 to 15 site visits that looked a lot like this, learning how to fly the drone and everything, we were able to collect usable data and create a method from start to finish with the UAV to get a stem per acre number just like the Freshwater Trust. This is the UAV we used. It's a 3D robotic solo equipped with a GoPro 4 and a gimbal. The Solo has a lithium-ion battery that allows for about 25-minute max flight time and a range of about 0.5 miles. So to begin our data collection, we first have to design a flight plan. We decided on 2 flight areas, one on the east side of the river bend and one on the west side. 2 flights are flown for each area, one parallel to the river and one perpendicular. I used a flight plan software called Mission Planner, where you're able to just enter the camera specs, flight angle, and your overlap percentages, and it just outputs a flight plan that is uploaded onto the UAV. We use 80% overlap and side lap of the photos. So overlap is achieved by the UAVs moving forward and the photos are taken at the right frequency to get 80% overlap. And then side lap is having the flight lines close enough together. We decided on 1 photo every 0.5 seconds to achieve that 80% overlap. Before the flights are flown, ground control points are laid down. Ground control points are points that are easily viewed from the photos being taken by the UAV. We use these 4 by 4 foot square black and white X's. And then the latitude, longitude, and altitude is taken in the middle of the X's. We use 10 of them placed throughout the area, if you can see the little red dots. That data is then input into the processing software to give the model location and scale. These are our flight details from the 4 flights. We put the camera angle at 45 degrees, and our flight times range from about 7 to 15 minutes. We ended up collecting about 4,000 photos, which was way too many. It gave us an overlap and side lap of like 90 to 100% when we only needed 80%. So we cut the amount of photos in half, went through and deleted every other photo. So we had about 2,000 total. The photos are then put into Lightroom to take away the fisheye effect and crop the distortion off the sides from the fisheye. Then they're uploaded into Agisoft PhotoScan, which uses the structure from motion algorithms to create the 3D model. In PhotoScan, I had to go through every photo and mask off the areas that weren't in the area of interest to cut down on processing time, because the computer I had was not big enough, and it still took about, well, it took me about 6 months, but like narrowed down, it was like probably one full week from start to finish of processing. Once the photos are masked off, then the ground control points can be entered. I also have to go through and put the ground control points on every single photo. It estimates it itself, but it's not exactly accurate, and the more accurate you want it, the closer the ground control points have to be to where they actually are. So once the ground control points are entered, then we can get a dense point cloud. This is just part of the point cloud that was output. We ran it on high quality, and using the structure from motion algorithms, we get a 3D model of the area. So once we have the 3D model, then we can begin to analyze it. We divided the whole area into 4 sections for analysis. 1 for calibration against the freshwater trust data, and then the remaining 3 for validation of the calculated parameters in that 1 section. We used section 3 for calibration because it had the most diverse terrain. So right now we're trying to compare our 3D model to what the freshwater trust counted in trees and see how accurate it is. So taking the point cloud, created in Agisoft, we uploaded it into Fusion, which is a LiDAR viewing and analysis software. In Fusion, you can view height maps of the area or navigate throughout to measure individual trees, and then a number of programs in Fusion were used to analyze and manipulate the point cloud. The First program used is the ground filter program. So right now the point cloud just contains data on the altitude of every point when you want the heights, right? So we have to differentiate between what is ground and what is not ground. So in this program, a surface is created in the middle of the point cloud, and then weights are given to each point depending on their distance from that surface and their position either above or below the surface. A certain number of iterations are run, and the ground points are chosen on the last iteration. So now you have a point cloud with all the points and a point cloud with just the ground points. The ground points point cloud is then used to create a ground surface by selecting a certain cell size and averaging the cell size number in that, or averaging the altitude number in that cell size. Using that surface model, a canopy height model can be created by subtracting the surface from the original point cloud. So you have altitude of the surface and altitude of the point cloud, subtract them, and you get the height, which is what we want. Next, you take that canopy height model, and for trees above 7 feet, input it into canopy maxima program, which is able to locate and measure tree heights. It uses a variable size window to find local maxima. It varies with altitude, so a larger tree will have a bigger canopy, so the window used to find the maximum will be larger. The parameter that predicts the accuracy of this tool is the cell size. So if your cell size is too small, the output will be too many trees. And if your cell size is too big, the number of trees output will be too small. So we had to calibrate that with the freshwater trust data. So we say this is how many trees there actually are here in section 3, so just a portion of it, calibrate the cell size to that, and then apply it to the rest of the model to see the accuracy of that parameter. For trees below 7 feet, we had to create a new method because of the resolution of the GoPro, and the canopy cover prevented many of the small trees from being seen. So what we did was clip the point cloud into points just between 3 and 7 feet and below 3 feet. Take those two clipped point clouds and create a canopy height model just like we did before. That canopy height model is then imported into ArcGIS, and the surface area of it is found. That surface area of the canopy height model is then used to calibrate a conversion factor using, again, section 3, the freshwater trust stems per section, dividing the surface area by the freshwater trust, getting a conversion factor, and then using that conversion factor to calculate the stems in the remaining 3 sections. So when we finally got stem count outputs from the point cloud, started comparing it to the freshwater trust data, we found out that the freshwater trust data is super low resolution. The sample size is super small. It's meant for monitoring purposes, not research purposes. So we had to create 2 methods of comparing it to the freshwater trust data. The first method just takes the 3 stem per acre numbers for each height class. So above 7 feet, it was 70 stems per acre. It applies it to each section, which isn't really realistic because there's not 70 stems per acre in the entire model. For the second method, we averaged the 3 closest transects to each section to get a different, unique stems per acre number for each section. So these are the results from the freshwater trust for method 1. You have 1 stem per acre number for each height class. For method 2, we're averaging the 3 closest transects to get unique stem per acre numbers for each height class. These are the comparison results between the UAV stem count output and the freshwater trust stem count output using method 1, so the 70 stems per acre. This is for above 7 feet. Our errors might seem high, but the average error is low. When you average the UAV stems per acre, it comes out to 69 compared to the freshwater trust average of 70 stems per acre. For 0 to 3 feet, I'll use this laser, our errors are pretty low. We predict this is because below 3 feet, the terrain is pretty constant and the trees are small, so it's easy to correlate the surface area with the number of trees. For 3 to 7 feet, the errors are higher, but again, the average error is not too high, and it still falls within the freshwater trust, that original 844 plus or minus number. So when you average all our results, the total error comes out to 0.31%, which is really good. But again, these numbers are stems per acre for the entire site, which is such low resolution that it's really easy to get within their interval. So with the transects averaged method, where we had different numbers for each section, for above 7 feet, our errors are really high. This is because of the resolution and the sample size. So you're only taking 3 transects per section. So in some transects, there was only like 1 tree that was above 7 feet. When you're averaging that out, it's just not realistic to what's actually there. For 0 to 3 feet, our errors range from about 10 to 24%, and 3 to 7 feet, the errors are negative 37 to 79%. Again, it seems high, but the total error for this method comes out to 21.6%. Doing a linear fit on that data gives us an R squared of 0.98. These are excluding the calibration sections because those errors were 0%. And then we ran a bland Altman analysis, the mean, which means our UAV method compared to the freshwater trust method will 99% of the time come within 159 stems per acre, which is within that plus or minus 844 stems per acre. So this pretty much says that the UAV is good enough for monitoring purposes. I also did a sensitivity analysis of using the different sections for calibration. So say we use section 1 instead of section 3, and it did show variabilities in the overall error. We had that 0.31% error. If we would have used section 1, it would have been 10%. And for the transects average method, it ranges from 11 to 35. This shows that there's variability in our method, but these errors are still within the expected interval that is needed. We also started working with a local company called OG Systems, who creates point clouds from aerial images. I just wanted to show this because this point cloud looks really good compared to our point cloud. So this is, and they can do it in like a day, where it took us a week to process it all. So hopefully we can move forward with them. The main limitations of this study were the resolution of the ground truth data. The reference data was for the entire area, so any error in the ground truth data was systematically applied to our data because it was calibrated with the ground truth data. The sensitivity analysis shows that there is added variability in choosing a reference section. The computer processing was very time intensive, and the repeatability of our below 7 feet method needs to be determined because it's a new method. We're not sure how well it will do in the future on the same site or on different sites. So in conclusion, the availability of the ground truth data was limited, causing some high errors. Our two analysis methods compared, the first one showed significantly better results than the second one. Our feature counting for above 7 feet is repeatable because it's been done before. For below 7 feet, it needs to be verified on additional plots. It will require calibration on new plots, and it should be tested longitudinally on the same plot again. When reproduced, it's hopeful that if we go to Cedar Creek again to compare the UAV to the ground truth data, it would only take 4 days, probably 5 or 6 days, from flying the drone to collecting the data and processing it to output a stem count. What we found was that our data generating a point cloud from a UAV was proven to produce outputs cheaper, faster, and with higher spatial resolution than the ground truth data at a confidence interval that was well within the acceptable error bounds. So moving forward, we have a paper in review for this study at the Journal of Environmental Monitoring and Assessment. The Rwanda study is happening. We'll probably go over there in the next 6 months to monitor the biomass attributed to cook stoves and water filters. We're also going to try and detect 3-stone fires with an IR camera on the UAV, and then work with the Freshwater Trust on more projects moving forward to try and do this method again, and then some species identification with IR and hyperspectral imagery. These are all my funders and acknowledgements. That's it. Any questions? Yeah?
I have a question about, it seems like maybe the canopy causes some problems with analyzing and getting the spatial data from the photos. Would it make sense to do this kind of research when the leaves have fallen off during the winter? Do you think that would be better data?
Yeah, we did actually do it in off-leaf, but that was a problem. When we first went out, I think there were leaves, and we had to like wait and figure out. It has to be the right time of year. Also, it can't be raining. But yeah, that's definitely a consideration.
Yeah, I was wondering about sort of the same thing, and if like how much that angle of observation, you said it was about 45 degrees.
Mm-hmm.
If that also has a big impact on how you're able to measure those trees below the higher above 7 feet.
Mm-hmm. Yeah. So right now, the research shows that the 45-degree angle is the best. But I've also seen a lot of people do one flight flat and then one flight at 45 degrees. And as low as you can possibly go is best to get the closest you can. Our highest trees were about 80 to 100, so we flew at 100 feet. But yeah, that's the hardest part.
So part of your equation, you used a prediction by TFT to divide essentially like the area into the amount of stems based on the images the drone captured. If you were trying to categorize a location for the first time and you were using the drone, where would the prediction come from? Would they have to do one session of in-person categorization to get that value?
Yeah, to get the TFT output?
Yeah.
Yeah, so you're gonna need something to compare it to, because, I mean, unless we move forward and see that these calibrated numbers are working on multiple sites or on the same site over time, then they're gonna have to use 1 year of calibration at least.
Okay.
Yeah. Anything else? Yeah.
Do you think you could use the drone to set its own standard? Because it seems like it might have been just as accurate or more accurate than TFT's process. Do you think you would be able to use the drone to set, maybe do a more extensive process to set a standard, like maybe every 5 years to compare it to, and then keep working off of that?
Yeah, and I think that's the idea moving forward, just to get as much data as we can, compare it to as much as we can to figure out what the best method is. And there's so much research going on right now on this stuff. It's pretty cool.
You had mentioned that the lower the drones fly, you tend to get better data. Is there any possibility of programming in some sort of like collision avoidance where the drone would fly below the canopy, among the stems, kind of define its own path based off some criteria so you can get better data that way?
Yeah, and that's, I mean, for the structure for motion algorithms, you generally want the photos to be at the same altitude.
Sure, sure.
But I know that some people are looking into that, like using small LiDAR sensors for collision avoidance and stuff like that. But yeah, that would be ideal to be able to get like all in everything to create the model. Yeah.
I have a question about the side overlap you were talking about. I was reading that usually for aerial photography, you just use about 35%, which is 80%. I was just wondering if it was why was like such a big difference, or like for drones, is the 80% a requirement, or?
What I've read is that 80% is the best to create the 3D model. So maybe what you read was just for like orthomosaics, right? So creating a larger photo from a bunch of smaller photos. But for getting accurate measurements from a 3D model, it was 80%. Yeah.
I have a quick question about the kind of social aspect of it. What kind of feedback, or did you get anybody talking to you about the research when you were flying drones down by Springfield, and what do you expect, like, the kind of social impact would be when you go over to Rwanda? Like, are drones being used for a lot of other research over there?
So what actually happened was my advisor took the drone to Rwanda to just kind of fly it around some sites at first and got in big trouble because he didn't ask. And they like pulled him aside when he was trying to fly back, and they were like, we saw you flying the drone, what were you doing? He had to pull out like all this research and say what he was doing. And then we went back again, and now they have this really extensive process for applying to be able to fly a drone. So we're going through that right now. And then here, I a few times ran into some people that were like, what are you doing? Like, one time we were accidentally too close to an airport without realizing it, which was not good. You have to be within 5 miles of an airport. Yeah, but the process is getting easier. It took us 6 months to get our registration through, because you have to, if you're doing research, you have to do this extensive application, but if you're just flying for fun, you can just fly it. And if you're a business, there's another application, but now it's getting easier and easier, which is cool. All right. Thanks.